Okay, so the other day we started with car making a turn on a road, and we saw a flat road. It's going like this. Right, so we have mu Sn is equal to mv squared over r, and then mu Smg. This gives you the maximum velocity that you can go safely, mu srg square root. Right, so in that problem, mu s was what, 0.6? What was the radius of the circle? 80 feet, I think. And then g was 32, right? Okay, so now, what was the answer that we got? 39.194. 192 feet per second. Okay, so now let's do the other extreme case, and that's if you're on a road that's 90-degree incline. Okay, 90-degree incline road. Something like this. Of course, no road is like that, right? But you've probably seen an application of this in the ride in Magic Mountain, where you go in a room and the room turns, right? And then the floor drops, okay? The floor drops on you, and then you stay stationary, but you're like stuck to the wall, right? Have you guys gone on that ride?
Yeah.
That's kind of like the opposite of the car on a flat road. Here, the normal force is pushing you in, and your weight is mg, and the friction force is holding you up, right, this way, so you won't slide. It's a bit similar to the problem we did where in chapter 5, right, where I had a block and another block, and then you exert the force, and then the force that you exert causes this to push on this, and then so it doesn't slide, right? So in this case, what's happening, it's a bit different. The thing is turning, right, which causes you to feel like you're being pushed out, you see? Where that's your inertia, because your body wants to go in a straight line, but the room is coming and trying to make you turn, you see? So you feel like you're being pushed out, and then that's providing the normal force instead of somebody pushing the block, you see? And then you have here mu Sn. So we can ask the question, what's the minimum velocity that it should turn? Not the maximum. Then what's the minimum so that the person does not slide down, right? What is V min so person slides, does not slide down, we should say. Person does not slide down. Okay? So then you're going to have USN is going to equal mg. And then N is going to give you the sufficient force needed. So in other words, in this case, look at how different it is from here. Here, the normal force is just supporting you so that you don't fall into the ground. It's the friction force that's allowing you to make the turn in a flat road. Over here, the friction force is supporting you so that you don't slide. But it's the normal force that's pushing you and allowing you to make the turn. It's opposite, their roles reversed. So N is equal to mv squared over r. And then I can substitute this, N is equal to mg over mu s. Then you can substitute it into here. and then R cancel. So this gives you V min. V min is equal to what? RG over mu S, right? V min is equal to RG over mu S, square root, right? What was the equation there? There the equation was V max is mu S RG square root. Here is RG over mu S square root. So if we use the same numbers, 80 times 32 over 0.6, let's see what that gives us. $65.3. Very different than the answer we got there. Here on a flat road, the maximum you can go is 39 feet per second, and the minimum you can go is what? Well, there is no minimum. The car can stop without any danger on a flat road, right? So V min is 0. Here, the minimum you should go is 65. You can't go any slower than that, otherwise you'll slide down, right? So 65 is way bigger than 39. So over here, you have to go very, very fast, right? So that you will not slide down. Now, what's the maximum you can go? If you go any faster, are you gonna start sliding up?
No.
Okay, it's like that block problem again, right? If you go any faster, what's going to happen? It's going to increase the normal force, right? Because you're going to feel pushed back more. This increases, but that doesn't mean this increases, because the friction force will stay equal to your weight, right? As long as you can go any faster, it doesn't matter. The normal force just increases, but the friction force equals mg, and then you don't slide up, you see? So then that's the minimum. Okay, the other extreme is, no, not the other extreme. These two are the extremes. The general case of this is a car on a banked road with friction. So car on a banked road. Car on banked road. So this is what we experience in our daily lives when you go on the road, and usually most roads will be like inclined at a certain angle. When you change like one freeway to another freeway, there'll be a slight angle to it, like this, right? So something like this, let's say. Theta, right? And so you're going like this. Now, how is this helping you? Because flat road, the problem is you're only relying on friction to supply sufficient force, right? To make a turn. Of course, you don't want to make the road completely 90, because then you're only relying on the normal force to make the turn. That's why we bank it at something, let's say 20 degrees or something. By banking it, what's happening is you're allowing the normal force to push you inward a bit, right? And you're also allowing the friction to help you make the turn. So it's like both of them are helping. Here, only friction. And then here, only normal force. Right? So now you're gonna create, if you're on a banked road, you're gonna create a range of possible velocities that you can drive at, right? Here, just like there is a range, but the minimum velocity is 0, the maximum velocity is 39. There, the range is 65 to infinity. You can go as fast as you want, okay? Here, you're gonna have a V min and you're gonna have a Vmax. So let's see what the idea of that is. If you go any slower than Vmin, you're gonna start sliding down, right? If you go any faster than Vmax, you're gonna start sliding up, right? So in order to calculate Vmin, for example, for Vmin, we assume that the car is going slow and it's on the verge of sliding down the ramp. But we don't want it to slide down the ramp, right? So if it's on the verge of sliding down, which direction is friction? If you're for Vmin, then the friction is up, right? And if we want to find Vmin, then we set friction equal to mu Sn, right? And then this is mg. So the free body diagram looks like this. And mg mu Sn, right? And which direction is the acceleration? The acceleration is towards the center, so it's horizontal, right? So it's this way. So this is different than a chapter 5 problem. For chapter 5, where we're doing the block sliding down the incline, they're different, right? Because we rotate the axis and then we do along the incline. Here, the acceleration is this way, so we keep the axis like this. So we keep it up and down like this, because we want the x direction to be in the same direction as AC, right? So therefore, the forces that we have to break into components, this is theta, right? And then the friction force, I'm going to redraw it from here, from the origin. The friction force is up the incline, right? So then, if that's theta, I can argue this thing is theta, right? This thing is theta. And then that's 90 minus theta. And then this is also theta. Right? So in these problems, we keep mg as mg. We don't break it up into components. So then we say here, in the x direction, we have n sine of theta like this. It's going to be this guy, and sine, right, that way. And then this component of the friction is opposing the motion, right? So minus mu Sn cosine theta, right? And sine theta minus mu Sn cos theta, and that's equal to what? M, this minus this equals mv squared over r, right? So, in other words, if the car is going at the minimum possible velocity, it's the normal force that's allowing you to make the turn, but the friction is fighting against you. The friction is fighting, how should I say? Friction is preventing you from sliding down, but in order to prevent you from sliding down, it's fighting against the component of the normal force that's allowing you to make the turn. It's a bit complex. See, when it's flat, it's pretty easy. You just say the normal force is supporting you, and the friction force is allowing you to make the turn when you're going at the maximum velocity, right? Here, when you're going at the minimum velocity, then is the normal force. In other words, the minimum velocity you get by saying the normal force is helping you to make the turn. The friction force is supporting you. So in a sense, maybe here's what's happening. The Vmin of the banked road is more similar to the 90-degree incline, because the 90-degree incline had a Vmin but didn't have a Vmax, you see? So the V min of a bank road, the dynamics of what's happening is more the incline. So because in the incline, 90-degree incline, the normal force made the turn, friction supported you. It didn't do anything else. Here, the horizontal component of the normal force is helping you make the turn. The horizontal component of the friction is fighting against your turn. You see? Then the vertical component, what's happening? You got n cos theta, this guy, plus the mu s n sine theta is mg. So the vertical component of the friction is supporting you, and the vertical component of the normal force is supporting you. So together they're both supporting, but in the horizontal direction, friction is fighting against you. And that's why you're not going very fast. In other words, because you're not going very fast, the outcome of it is that friction is fighting against you, so you won't slip down. Okay, now we're gonna solve for the V min, right? So then you can substitute for n here. Factor this out, put it on the bottom, solve for n. And then take that and substitute it into the top end. Right? So then here factor out the sine theta. Right? And then factor out the n and then substitute this guy in there. And then the m and the m cancel. So this gives you the equation for V min. Okay, now if we did that correct, what's going to happen if I put theta is 90? If theta is 90, then it's going to mimic a road that's vertically inclined, right? So if I put 90 in here, what do I get? V min, I get sine of 90 is 1, cosine of 90 is 0, cosine of 90 is 0, sine of 90 is 1. So I get 1 here and 1 down here, right? So I literally get Rg. So if this is 1, and this is 1, and the other two are 0, right? So you get Rg over mu s. That gives you the V min of the vertically inclined, right, surface. But I'm not going to put 0, right? I'm not going to put 0 because for the 0 degrees, there is no V min. You can stop, right? So I only have a V max for that one, right? So this gives you the general equation on any road, right, that you can drive. Now the maximum velocity is going to be the velocity where if you go any faster, you're now going to slide up the hill, right? So in that case, what happens? You slide up the hill, and then the friction is down just before you slide up the hill, right? So now what happens? The friction switches on you. And now this is theta. So what happens? Now the role that friction is playing changes, right? So it's going to be in the horizontal direction. This is the vertical direction. In the horizontal direction, it's going to be n sine theta plus mu s n cosine. Okay, now you're going at the maximum, right? So it's more acting like the car on the road. Friction is actually helping you make the turn, not fighting against you. But also the normal force is helping you make the turn. They're both facing this way, right? It's like taking this, inclining it. Friction is this way, and the normal force is this way. They're both to the right. You see? So they're both helping you. But the role of the friction in the y direction changes. Now it's n cos theta minus mu s n sine theta. In other words, what happens is friction now, instead of supporting you from going down, friction is like causing you to want to go down more, you see? Because your car is on the verge of, because you're going too fast, and your car is on the verge of sliding up, so the friction is actually pushing you down more in the down direction. Isn't that weird? Yeah. So, so what's that going to do to the normal force? Cosine theta minus mu s sine theta, right? So the normal force is a minus down here. So which means the normal force is what? Bigger than it was in the other case, right?
Yeah, you go over the bottom.
Yes, it's a subtraction. So you might say, well, what's happening here? What's the order of events that's happening? Is it the friction is changing direction on you, and then that's causing the normal force to change? The answer is more like this. It's because of what the car is doing, the driver of the car. He's the one determining which direction the friction is and what is the normal force, right? If your car is going slow, you tend to not push on the road that much, right? You tend to want to slide down, right? So if that's the case, you don't push on the road, the normal force is less, and then the friction is up, right? So if you're not driving fast, this is going to be plus. It's going to reduce your normal force, right? So it's not so much friction that's the decider, it's the driver of the car that's deciding what's happening. If you're going very fast, your car is pushing on the road very hard, right? Now the friction is down because you tend to slide up, right? So now the friction is down, it increases the normal force. Then when you put this into this equation, you get a minus here, but then this is plus. So the sign of the two things changes, plus and minus. So the top becomes plus, the bottom becomes minus. So V max is going to be So now to mimic the flat road, I can put theta 0 into this, right? So theta is 0. And then sine of theta is going to be what? 0. Cosine theta is going to be 1, right? So this guy is going to be 0. And this guy is going to be 1. 1. Well, then you have mu s rg, right? Then you have back the result that we have. Cool. So now let's put in the numbers. Let's say the road was inclined at 20 degrees, or 25 degrees, let's say. If theta is 25, what's going to be V max? So it's going to be square root of 80 feet times 32 times sine of 25 plus 0.6 cosine 25 over cosine 25 minus 0.6 sine 25. so put that all in, let's see what we get. Calculate that. .56 feet per second. Which is 41.98 miles per hour, so pretty much 42 miles an hour. So the road condition should be that you can go at 42 miles an hour. Huh? But of course, if it's rainy, you gotta go slower. So that's the maximum you can go. And then the minimum you can go is gonna be square root of right? So the signs switch. You put a minus on the top and a plus on the bottom.
That's because friction just places the other way, right?
Yes, exactly. It switches its role.
I have a question.
Hmm.
If a car is going straight and it's raining, does the friction still decrease?
If the what? If the car is on a
Is
flat
the tread-
road?
Yeah, it is moving straight and it's raining.
And say that again. If the cars are going flat road and it's going what?
Straight, it's not pouring.
Oh, it's going just straight, not making a turn.
Does the friction stay? Does it make a difference if the friction is
Well, then there's only friction along the direction of the tire. There's no. The friction that I'm talking about is the friction that's perpendicular to the direction that the car is going. See what I mean? The friction that allows you to turn. Yeah, I'm not talking about like, let's say when I walk, there's friction that's opposing me. But when I walk and also make a turn, there's the friction that's allowing me to turn. I'm focusing on that friction, the perpendicular. Yeah. Anyone got it?
Barely got things right in.
I'm too lazy now. Oh, it's negative. So it's gonna be, this thing comes out to be negative.
Yeah.
In which case, that means the car can even stop. That's a good thing. It doesn't, it can go so slow that it can stop and the friction is sufficient to, yeah. So because the coefficient of friction is big and the angle of the incline is is too small. So there's no danger of it sliding down. So no danger of sliding down. So it's kind of like the flat road scenario where you can go as slow as you want and even stop. because angle is too low and also the friction is too high. It's sufficient friction.
But if it was raining, that could change it.
Yeah.
So that would reduce the.
Yeah, exactly.
And no, you could be parked and all of a sudden your car could start to slide away.
Yeah.
Ah, look,
This is another good one of a circular motion problem. The one we did, the ones I'm doing now are examples of circular motion where the plane of the circular motion is horizontal. So the car, or it could be a perpendicular road, and it's going like this, right? So the plane of the motion is like this. So I'll do one more case like that.
So, like, this is kind of like, you ever see like those rounded cages where people drive a motorcycle?
Oh yeah, I was gonna say, the rounded cage is another example of the room.
Yeah.
The same physics as the room dropping where the floor
Well,
drops.
it's actually an example of everything in between that. Like, because they start off at the bottom.
Yeah, you're
and
right.
the angle
The
increases,
motorcycle, right?
and
You
the
kind of
speed.
daredevil
Yeah.
motorcycle. So but when you're down here, the normal force is pushing you like that.
Yeah.
You got mg. So it's a car on a bank road. Then you drive fast, and then you go like this. But then when you go over here on the top, the normal force is actually pushing you down.
Yeah, I don't think they go that high.
Do they ever go above
I don't
the
think-
middle?
I think just a little bit, but not much.
What would oppose gravity then?
No, that would be hard to go. That would be hard to go in a circle
Yeah,
like this.
I've never seen them go that high.
But they can probably do this.
Oh yeah.
Yeah, they do that a lot.
They go like this, almost like an electron in an atom.
Yeah.
You know, they
Yeah.
could probably do that, but it's very possible to do this.
Yeah.
Because then the normal force is pushing down and the mg pushing down.
Yeah, I've never seen them go that
And
high.
centripetal would be like over R and have
Yeah, but then what's going to prevent you from?
I guess friction would be the only thing.
Let's see, friction would be this way.
Yeah, barely.
You know what? It might be doable. The faster you go.
You have to go really fast though.
Yeah.
Yeah. So
But
like,
not impossible.
maybe he can slow. He can stay for like
You have to be going
Very quick, right?
Yeah, very quick.
Very hard to
You
go
have
up
to be
there.
going
Yeah.
at a crazy amount of speed too.
Yeah, but this one is more doable.
Yeah,
like
they
the
do that.
motorcycle like this,
But like
this.
they have to start off at the bottom slow and build up speed before they're able to go higher up on the circle. They don't start off at like otherwise if they went too slow they'll fall right over it. That's just what's going through my head right now.
Is it called Daredevil?
I think some people call it like a cage of death or something. Yeah, just yeah, there it is. Motorcycle, okay. Let's see how high they go. They got like a speed.
You see, that's pretty much vertical right there.
Yeah, that's what you were talking about.
Yeah.
So yeah, I don't think you can pick up speed to go any higher than that. Dang, this is why they call it cage of death.
Oh, now two motorcycles.
Yeah, they gotta avoid each other and do this.
I'm getting headache just looking at it.
Yeah.
Cool.
I know him.
And oh, no hands. Oh my God.
Dang, that was
I mean, if you fall down.
Now the one that you're seeing that's like this, that's like a vertical.
Yeah.
Circular motion in the vertical plane. You see?
slow down. They can't just stop, otherwise they fall.
Yeah, they can't just stop. They have to sort of slow down and. Oh, third one?
Yeah.
Okay, good luck.
Oh my gosh.
So so they gotta
Oh,
sync
they
up.
first did the hydrogen atom, then the helium atom,
Yeah.
and this is right.
They gotta like.
This is lithium.
Listen.
But wait a minute,
Yeah.
shouldn't the third one be in a farther away? 1s,
Yeah, yeah.
2s.
Yeah.
By the time you do 2 electrons, you gotta be farther away, right? 2p, and then the other one they should do 2, like this one, the 2p1, 8.
Yeah, it's like looks like two of them have to sync up.
Wow.
Wait a minute, they're defying the, yeah, they have 3 electrons in the same orbital. Imagine the fourth one. Oh
I wouldn't even try to tell me.
I can understand this is a bigger dome, but damn.
Oh man. Bro, that should be very good.
So extra credit if you guys can do this.
How many?
Automatic, you pass the course.
Whoa. Damn.
Okay, fifth one, come on. Don't be wimps.
Oh. No way.
I can't believe this. How many electrons can they put in the 1s orbital?
At least not more than half, I don't think. Because then afterwards, not
Yeah,
many
there
people
would
will
be
have
enough room.
Yeah.
They have to be constantly alternating
Yeah.
like that. Like
I guess.
one would have to like do that while the other four go
Well,
on.
how do you know that you're going like this, someone else is going like this? You
Yeah,
can crash easily.
Yeah, it's just they must have got the timing down pat.
Okay.
I kind of like, alright, now it's time to let people up.
Copy crash.
Wow, that's pretty good.
They probably crushed the whole thing with it.
Oh yeah.
Yeah.
And if I just split their team up 2 and 2. Like one learns the left side and one learns the right side.
Okay, good
And
job.
then
Wow, that was good.
they combine it at the end.
Now let's go to a more entertaining video by yours truly. Where was that?
It should have been
Okay, well, so I have this ring here. The diameter is 26 centimeters, right? And I have hit the post to it, and then I can rotate this about this post at a certain period of revolution, right? So I can say based on the period of revolution that I do, the quicker I do it, the farther up the ring the beads will move, right? So if I do them really quick, okay? You see, they're kind of around here. So if I do quicker, they can move higher up the ring, right? So based on a certain period of revolution of that, right? So the beads are somewhere around here. So what I want to find out is calculate what is their location depending on the period of revolution, right? The period of revolution, we're going to measure that in seconds, right? This is the physics of this, right? Okay? So we have a free body diagram of the object will look like this. It's on a ring. Okay, let's do let me see if I actually did it. Then we'll do the equations. That we are using, right? So in my resting, go. 1, 2, right? So I count a certain number of revolutions of the period, and then approximately notice where the beads are resting. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
Is this so,
Okay? So
This
it's
is
kind
so
of hard to do
entertaining.
this because I'm trying to both time it and do the revolutions. So let's do that again. It came out about 9 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so 8.5 seconds. So 20 cycles is taking 8.5 seconds, 5 seconds. So in the physics problem, what they'll tell you, they'll actually tell you, you have a ring, they'll give you the radius of the ring, they'll give you the period of rotation of the ring, and then they say, well, what is the angle? Or they might ask for the little r, right? So once you know what the angle is, you can always calculate the little r, right? In my case, we actually measured the period, and then we're going to put it into here, right? And then find out what our angle is going to be.
okay, so based on that video, then we have the radius was given, right? The diameter was 26 centimeters. So here, as I am rotating it, the inertia is causing it to move out, right? Until it settles in a nice place. So the physics of it is not too far different than the car on the banked road. Here you have the normal force pushing this way towards the center. And you have the mg. And probably the friction is minimal because the beads, they don't really touch with the thing too much. The friction is very, very minimal. So you just have N and mg, and then we want to know what this angle is going to be, theta, right? Calculate the angle of theta from the vertical. And instead of the velocity being given to you, the period is given in this case. How many seconds is taking, period, is how many seconds for one revolution, is seconds per cycle. Right, so in my case, what I did is I timed 20 cycles, right, and I got 8.5 seconds. So that would be 8.5 seconds per 20 cycles. And then that would give me 0.425 seconds is the period, right? So then what's the dynamics of this? So now this component, this angle, if that angle is theta, this is also theta, right? This component is n cosine theta, and then this one is n sine theta. Right, so you have n sine theta is equal to mv squared over r. That's going in a circle, right? And then here, n cosine theta is equal to what? mg. Right? Then you divide these two. You get what? Tangent theta is equal to m cancel, v squared over rg.
I have a question.
Yeah.
So v squared over r is centripetal acceleration, right? So
Yes, centripetal acceleration.
So why is n sine theta equal to centripetal acceleration?
Because it's accelerating this way, toward the center of the circle. See, it's making a circular motion
Oh, around. Okay, I saw. So
around
circle
like
around
this.
there. Okay, I see.
And so it's going like this, so the normal force is this way, right, towards the
Yeah.
center. Now, what is this radius? The radius is this distance from here to here. It's not the radius of the actual ring, right? So this one, let's write it as little r. So that would be this distance right here, okay? R, depending on how far up the beads went, right? So then what's little r in relation to the radius of the ring? Then that's the little r is going to equal r sine theta, right? This theta is right here, right? So little r is big R sine theta, so then I'm gonna change that here, right? So we have here tangent theta is equal to v squared over r sine theta times g. So it's a little different than the car problem in the sense that the radius is changing as I'm twisting it up, so it's going up.
I don't know. Why we put the normal force as the ring? Like why do we do like that?
How else would you do it? Because as you're turning the bead would push out on the ring and the ring will push this way. It's kind of the same thing as the car on the bank road.
Yeah. It always goes to the same thing because it stays on. It's kind of like
What's this?
Which direction would you make the normal force?
I would do it perpendicular.
Yeah.
You,
Okay, I see.
you want to put the normal force up like this?
No, you want it perpendicular to the surface.
Yeah, to the surface, yeah. So as the thing goes up, the normal force gets more and more bent like this. Yeah, exactly. Perpendicular to the surface. Okay, so now we got what? This thing goes up. So we have, does that cancel? We have sine over cosine. Doesn't really cancel, huh? We have tangent theta times sine theta is equal to v squared over rg. But now I need to write this in terms of the period of the circle, right? The period of the cycle, not the velocity. So how do I do that? So then the period is going to be what? The velocity is going to be the distance that it went divided by the time that it took, right?
Yeah.
So velocity is distance over time, and then the distance is the circumference of the circle, so which is 2 pi r over the period t. So then you put that over here. Ooh, you got so many things going on. So you got tangent theta, sine theta, v is equal to 2 pi r over the period t squared over rg. Okay. So then you have here tangent theta, sine theta is 4 pi squared r squared over rg period squared. But then r squared is going to equal, right? Where was that equation? R was r sine theta, right? So I need to square that again. R squared sine squared theta, right? So the r appeared twice. One because it was in the radius of the circle. Then I rewrote the velocity in terms of the radius. So then it appeared again. Now I square that. So now let's simplify. R cancels r. Sine cancels sine. Oh, that's nice because now this is sine over cosine, right? Sine over cosine is equal to 4 pi squared over gt squared r sine theta. And then sine cancels sine. And so therefore the equation becomes cosine theta is gt squared over 4 pi squared r. Which, was that the same equation in the video? Yeah. See? Cosine theta gt squared over 4 pi squared r. Then we can test to see if it gives us a reasonable answer. Cosine theta, G was 9.8. My period was 0.425 seconds. Then I square that. Then 4 pi squared. The radius of the circle was what? Did I write it somewhere? It was 20.
Oh, the diameter was 26 centimeter for that ring. So the radius was 13 centimeters. Right? So I changed the radius to 0.13 meters, right? Then I calculate cosine theta. Let's see what happens here. They'll actually tell you, you have a ring, they'll give you the radius of the ring, they'll give you the period of rotation of the ring, and then they say, what is the angle? Or they might ask for the little r, right? So once you know what the angle is, you can always calculate the little r, right? In my case, we actually measured the period, and then we're going to put it into here, right? And then find out what our angle is going to be. Okay, so we have here cosine, this is 9.8, right? So the period is going to be 0.425 squared over 4 pi squared, and then the r is going to be half the diameter of the ring, so that's 0.13. Okay, so let us calculate that. Degrees, 69.8 degrees. So it's quite high. It was somewhere here. Predicted angle, 70 degrees, right? That was kind of similar to what I had when I did it, right? When I did it, where was it? Where were the beads? They were kind of like, visually, you can see that the beads were around here, right? Something like that. So you can kind of see, okay, if the angle was 69.8, the other problem, the other thing that the problem can ask is, what is the r value? What is the little r? So then the little r is going to be r sine of theta, right? So then we can say r is going to be the 0.13 sine of 69.8. Okay? After that, it's just calculation. Okay, so then what I could do is I could say, okay, I can go like this, and then kind of make a visual note of where the bead is at. Okay, then it's somewhere here. Then I can measure the distance between that and the center, so 12.5 centimeters, right there. Okay. It's very visual, very rough. So my experimental R came out to be 12.5 centimeters. So of course, it's kind of visual. You're kind of doing that, and you're trying to guesstimate where it is. And then my period itself is kind of not exact because I'm by myself doing it, but you can kind of get the idea of the problem. So what do we learn from this problem? The bigger the period, if the period is big, what does that mean? Okay, that means you're going slow. It's going very, very slow. So if the period is big, what's going to happen? The angle is going to be very small, right? Because they're going to be kind of down here. So this angle is going to be small. When the angle is small, cosine of the angle is big, right? So when the period is big, cosine of the angle should be big, and that means the angle is actually small. So that the equation you derive should make sense in limiting cases. So then as the period goes smaller and smaller, what happens? The cosine of the angle goes smaller and smaller, and then the angle gets larger and larger. So the angle gets larger and larger means that this angle starts getting bigger, 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 and the thing then goes up all the way like this. Now, can the thing ever go more than 90? Right? So let's say you're doing so fast that the t almost approaches 0, right? The t approaches 0. What's the greatest that the angle can be, right? So we can say here, the limit of this as cosine of theta is 0, what happens? Theta is 90. Theta begins to approach 90. So that means no matter how fast I do this, it can never actually go like this and then supersede the 90. It can kind of approach 90 like this. So that means if I'm going very, very fast, the period goes down to almost 0, right? But the angle can't get greater than 90. Right? So you can never actually reach 90, right? But you can kind of get close to it. This is almost like the problem of, you can have a similar problem with
90-degree incline or...
It's like the 90-degree incline, yeah. Where students, where children and kids sit on a chair, right? And there's a post like this, right? And then as they speed up, the string starts getting higher and higher. The physics of this and the physics of this
is exactly identical. Instead of normal force pushing you up, it's the tension in the rope, right? And then you have here, this is R, and then this is the little r, right? So the same, pretty much physics holds true. So if you spin the person very, very fast, the greatest angle that they can approach, right? The greatest angle they can approach is close to 90, but it can never exactly equal 90. So maybe it's going to be like something like 80, 88 or 87, right? No matter how fast they go, they never go close to 90, they never exactly equal 90, and they never pass 90, okay? So I hope this helps you understand the physics of these kinds of situations, then you can apply it. Okay, let's see if I did, the next ones are the,
It's because like at 90, the normal force is completely like perpendicular, right?
Yes.
So there's nothing you can't move back up anymore.
yeah.
Because it just goes like dun 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 and stops here.
Yeah, it stops there, yeah. Okay, now let's do a vertical circular motion. So those would be cases where, like you saw in a motorcycle, where the motorcycle is going like this. Circular motion where the motion is in the vertical plane. I've classically called this problems the revolution type ride and colossus, but right now there's more. Those are the rides that were famous when I was a kid. Now there's so many other rides: revolution ride and magic mountain. I don't know. Is it even open anymore?
Yeah, I think so. I think they made it like R2 or something like, or X.
Yeah, so the revolution type of ride is where you're going,
Your favorite restaurants now deliver with DoorDash.
what is called a new revolution. I've never gone on this because I get scared of them. I guess this is the closest I can come to.
But you know the physics of it.
I know the physics of it, but that's why I throw up. Right, so it has to gain potential energy, right? It should go a loop like this, right? Isn't it?
There it is.
Oh my God, that's scary. You're upside down, basically. So that's the kind of ride where you're going down, and then at the top you're facing down, right?
I feel like
there's Tatsu. It's pretty good because they aim you straight down. Like they sit you and then they turn you so you're facing downward the whole time.
X.
Yeah.
X there. Down.
Tatsu. You sit and then right before it goes, it turns you up. So you're looking down.
Yeah, right.
So then every drop, you're looking straight down like 100 feet.
Yeah, right. Yeah, I tried that one.
So,
Yeah, 'cause if you-
what's happening at the bottom of this ride and what's happening at the top? Let's focus on the two extreme cases.
So,
At the bottom, we've got the normal force supporting you, and we've got mg,
it's equal to M.
and then acceleration is towards the center of the circle, right?
Alright.
So we have n minus mg is equal to mv squared over r. So the normal force that the seat is supporting you is larger than your weight at the bottom. So n is equal to mg plus mv squared over r. So let's see what happens. If the ride stops at the bottom, this is at bottom, is there any danger for the ride stopping at the bottom? If v is 0, what happens?
N is equal to
N is equal to mg. That's okay. That means you can stop, nothing happens to you. That means your apparent weight equals your actual weight. Apparent weight is the normal force, right? If the v gets larger and larger, right? As the v gets larger and larger, the normal force increases. That means you weigh more than your actual weight,
Is that why you
right?
feel pushed down?
Yeah, because what happens is as you're going down, you feel like you're being pushed down. And then the ground has to exert a force to change your direction. You see? Like that. So the ground has to exert the force. It's a bit similar to the dynamics of what happens when when you get in an elevator, and the elevator has to accelerate up. And the ground of the elevator has to push on you greater than your weight. But it's different in the sense that here, you're not actually moving up, you're moving this way, you see? But your acceleration is that way though, you see? So you're coming down very fast, and then that force here pushing you up has to push you up greater than your weight. So in terms of physics, it's the same as the dynamics of the elevator accelerating up, you see? So if you put a seat, scale underneath you, you're gonna weigh more than your weight, okay? So if you want to design, usually probably most rides are designed so that people weigh maybe twice their weight or 3 times their weight. So if we want n to be 3 mg, how fast should the ride go at the bottom? This would mean you're feeling 3 g's of force at the bottom of that ride, right? So then you put 3 mg here.
2G.
Then what happens? 2 mg, and then v is equal to square root of 2gr. That means you should design the ride so that the velocity at the bottom equals square root of 2gr. And then people will feel 3 times their weight. 3 g's of force at the bottom, right? So if that's the case, where should the ride initially begin? See, if we rewind this, is this where the thing started?
Yeah.
So imagine before they started, pause it here. Okay, so pause it there. Right at that point, the roller coaster is like right here, right?
Right.
Then it's gonna go eventually like that. So how high should this be so that when you're at the bottom here, you're going this fast?
Conservation of energy.
You can do conservation of energy, potential energy, kinetic energy, right? You can say, okay, if we want V to be square root of 2gr,
Right.
right? So given this radius, let's say r, what should the initial height be,
mgh.
right? So we can say the potential energy here is equal to the kinetic energy here.
1/2 mv.
1/2 mv squared, and then v squared is going to be what? 2gr. In other words, first you say, if you're the engineer of this ride, you say, what do we want people to feel at the bottom? You start from there. You say, oh, we want to design the ride so you feel 3 G's of force. Then based on that, design your radius, and then based on that, do the energy. 2 and 2 cancels, G and G cancels, H equals what? R? Wait, that seems too small.
Yeah, you can change it to.
That means the car should start here.
But it's not gonna go to the top.
You know what the problem of that is?
Yeah.
It's not gonna even make it to the
Yeah,
top.
it's just gonna go up to like half the circle.
Yeah, it's
and
gonna
then
go
stop.
like this and then it's gonna stop here. People are gonna fall.
Yeah, and then go back.
So that means we should design the ride so that people don't feel 3 G's of force. At least they should feel 5 G's or 6 G's of force.
Whatever they want to do,
At
just make
least
sure
like-
at top they stay on the.
Okay, so then let's do the top, the physics of the top. What's the physics of the top? How minimum should they go at the top?
Right.
So at the top, what's happening?
Assume there's no friction and then. Like
Yeah, we're assuming there's no friction on the tracks.
2R.
So at the top, we've got the seat pushing you down, and we've got mg down. They're both down. So we have n plus mg is equal to mv squared over r. Both of the forces are down, right? So now, the most minimum velocity should be where the n is 0. You never want the normal force to be less than 0, right?
Right.
So if n is 0, that gives you the minimum velocity that you should design that ride. But even that's dangerous because n is 0 means you're about to fall off, you know?
Yeah.
So V min is square root of Rg. But usually you, in practical real life situation, you would probably design it so that at least people will feel their weight or maybe a half of their weight, something like that. If the most minimum may be half their weight.
That's the reason that we're doing like a few roller coasters is that when they drop, they don't always. I think I've only seen like 1 or 2 that go fully like down straight.
Oh,
But there's only like a few that actually.
that goes straight down.
Yeah. Instead of like at an angle, is it because like you guys do it too much?
Yeah, because the normal, if you go straight down, the drop is, the acceleration is very fast, and then your heart just sort of, even the acceleration of G is a lot for a lot of people.
Yeah.
That feeling, acceleration of the feeling of the normal force is going to 0. Because as soon as I drop you, your first feeling is like, the normal force drops to 0, you feel weightless.
So,
That is an awful feeling. I can't do that.
so it would be that
Drop
plus
Lagoon has
the acceleration of
Huh?
the roller
a
coaster.
just fall straight down.
Yeah, the free fall, right?
Well, like a bungee jump.
Huh?
Like
A
a
bungee jump.
Yeah.
That's
But
bad.
if it was on a roller coaster, it'd be that
my favorite.
feeling of bungee jump plus however fast the roller
However
coaster-
fast you're going.
Yeah.
Like a video.
But I mean, they do have like the free fall ones, but they just drop you like this and they slow you down. There's a deceleration. It's not a roller coaster on a track; they just rise you
Oh,
up.
it just rise you and then just drop
Yeah,
you.
but
yeah.
they also decelerate you. They don't just let you hit,
Oh,
stop.
yeah, yeah,
So it
of
slows
course.
down toward the end.
Yeah, of course.
You
You
feel
can't,
it.
you can't fall.
Yeah, it'd be falling to your death.
So let's say you design the ride so that at least you feel half your weight at the top. So then this one will be, n will be equal to half mg. Then what's gonna happen? Then that gives you? Half mg plus mg, right? Half mg plus mg is equal to mv squared over r. Then that's gonna equal 3 halves mg, mv squared over r, and then mm. So v should be, v at the top should be square root of 3 halves gr. So we can call this v top practical, practical, whereas that one is a bit dangerous, right? So now if that's the case, if the v at the top is square root of 3/2 GR, what should your V over here be? We could also do another potential energy, kinetic energy conservation, right? The kinetic energy here, half mv bottom squared, right, is equal to the kinetic energy there plus the potential energy there, right? Half mv top squared plus mgh. In other words, now we're working backwards. We're saying at minimum you gotta go this speed at the top to be practical, right? V top practical. Then we're saying from there, what should your velocity at the bottom be? Assume there's no friction on the tracks.
You can just set it equal to the beginning though, right?
Right? Well,
You can just set it equal to the first gravitational potential energy.
Got you.
which one?
Just
So
set
you
the
set it
first-
to the beginning, like, which is mg delta.
Oh, you mean set it equal to
Yeah.
that? Yeah. Yeah, or I could just do it this way. Yeah, it doesn't matter. Then you can say here half V bottom squared is half V top is squared is going to be 3/2 GR plus GH. Well, what is H? H from here to here is twice the radius, right? So that's going to be here 2R. So then you're going to have what here? I can multiply everything by 2. Multiply everything by 2. You're going to have what? B bottom squared is going to equal, multiply this by 2, so 3/2 GR plus multiply this by 2, so 4 GR. So B bottom squared is equal to, what is that? 8 plus 3, 11 over 2 GR. Oh, so that means, you see, this was way too low for V bottom. It needs to be 11 over 2. This is 5.5. This was 2. Way too slow. You would never make it to the top like that.
So like if you were an engineer, you would focus on the top first, and then
Yeah, you focus on the top, then focus here, and then design the height from there, right? So in which case, what are people feeling? How much weight are they feeling down here? Here they're feeling half G's of acceleration, half a G. How about down here? Then you go back to the bottom equation. Then you say, okay, mg plus m over r, because also you're considering G's. You don't want, if you're an engineer, you don't want people feeling too many G's, right? So you don't want them getting sick. So then you put the V bottom squared, which is half over 11 over 2 GR, and then you square that, right? So then that's going to be here, R cancels. That's 5.5 plus 1, 6.5.
Wait, is that 1/2 mv squared?
What's that?
Isn't kinetic energy 1/2 mv squared?
Yeah, 1/2 mv squared, but I multiplied everything by 2 to get rid of that 2, and that canceled this 2, so I'm left with 3/2, and this became 4.
Oh, I thought you were calculating the height. Never mind.
Yeah, no, I'm calculating first how much people would feel here.
Okay.
So can people handle 6.5 G's?
I think so.
Because then if they can't, I would need to go back and say, oh no, over here let them feel quarter of their weight, manipulate it. You know what I'm trying to say? So if you're really designing this as a ride, so you look up, you say,
You might be able to withstand it for that split second. Maybe not an extended amount of time at 6.5 G's, but there's that one ride, I think Superman, that just takes off at like 0
Yeah,
to 100
so-
miles.
see, how many G's can a human take?
46.
Well, that's too much. This is the guy who fell from the outer space. Air Force Officer John Strap, 46 G's.
46 G?
Wait,
46 G.
then like let's
There are
say he
isolated incidents of humans surviving abnormally high G-forces, most notably the Air Force officer John Strapp, who demonstrated a human can withstand 46.2 Gs.
So wait,
That's a-
let's say he weighed 200 pounds. His apparent weight would be 9,240
Yeah.
pounds.
What after that guy?
Because you feel heavy, you can't even.
You can't even move at that point.
Well, a ton basically.
Yeah, but
200-pound man would basically weigh a ton.
See, astronauts normally experience a maximum G-force of around 3 Gs during a rocket launch. So even that's not a lot. Huh?
Well, I wonder what's the G's on like. There's a Rise Superman where
That's right.
it takes
Yeah.
off from like a 0 to.
The top paragraph says a typical
100,
person can
like,
handle
seconds.
about 5 G, meaning some people might pass out when riding a higher G roller coaster, which in some cases exceeds. Something tells me 6.5 Gs is too much.
Yeah.
So then we would have to go back and redo this to maybe a quarter G here, right? Then maybe that's gonna lessen the load on this V, and then you can say more reasonable. Like I want to maybe make this 5 or 5 G maybe, you know.
So you would
Or
lower
we could
the
adjust the
effective weight
radius
on
of
top,
the
maybe.
loop.
Then you go back and change the effective weight on top.
So the-
But you want to make it a little larger than this V min at least.
Okay.
Well,
right,
what
yeah.
do we set
On the
the?
right side, why is the 2 squared, not the 3 over 2? Isn't that the, isn't 3 over 2 the?
Yeah, 3 over 2 is the V top squared, which is this guy. And then you got the half from the kinetic energy. And then the 2 I just multiplied to get rid of this 2. Okay, let's just say you were fine with that. Then you could work backwards and calculate what height you would need, right? So then you would go back to here and say, okay, GH is equal to half. And then you would say here V squared would be what? 11 over 2 GR, right? 11 over 2 GR. Then what would H be? 11 over 4R, which would make it what? 2.75 R. So 3R almost. So visually, what would that look like? The height. 1, 2.75. So roughly around here. Like that, huh? So it doesn't look that high actually, because it's only a little bit above this. You see? But even with that, you're still going a bit too fast here. But remember, we're assuming there's no friction on the tracks. With friction, you probably have to start a little bit more up, right? Because you're going to lose some energy due to friction. So,
Yeah, I looked it up. Superman's only 3.6 Gs.
even Superman is only 3.6
Yeah.
Gs. So our
Yeah.
6.5 Gs is way too
Yeah.
much, huh?
Yeah,
Fixed too.
because that one's pretty.
That's 4 Gs.
What?
The fastest route you have over there?
It's 4 Gs.
4 Gs.
So yeah, at 6, it's 0.5.
But
I wonder if we made it a quarter, what would happen up here? If we made this a quarter, we would say this one would be a quarter. This one would be 5/4. Let's see if that's gonna fix things.
I would change the
And then
ratio.
this one would be 5/4.
It doesn't really matter, like, when you calculate that, if you use the minimum, that's gonna give you 5G, at least.
What is?
I mean, if you use minimum, like, let's say normal.
Oh, did you
0,
try the minimum?
Yeah, that's just 5G. At the end, yeah. 5. Or 6, yeah.
This is just the
Still
problem.
pretty high.
5/4. If we do 5/4, then it's gonna be 5/4 plus 4.
So you just found it when the.
So it's gonna be 5.25.
Yeah.
Yeah, okay.
What?
Yeah, you're right. If you feel a quarter of your weight at the top, you feel 5 1/4 on the bottom.
Well, why would we want it? Like, shouldn't it we're being thrown like away with the centripetal force. Why would we want to be still pulled downward when we want like our weight to be current weight to be zero, the n be 0 or
No,
less
you don't
than
want
0?
n to be 0 because if n is 0, you're almost falling down, and the only thing keeping you from falling down is the seat belt.
Oh, okay. Now
You
I
wanna
see.
be
Oh,
like
the
that?
end's pointing the wrong way. Sorry.
No, yeah.
Yeah, I forgot it flipped.
Yeah. You don't want the seat belt to be only your
So then-
security.
So then you want it closer to why are we making it smaller? Shouldn't we make it bigger? Shouldn't it be like
Yeah, but I'm trying to make this as big as possible so that this V is not too big, so that people don't feel 6 times their weight here or 7 times their weight. See?
okay.
But then you have to remember that this is all very split second.
Yeah,
So it's not a sustained G. So maybe it is okay.
that's true.
Yeah. It's a very split, then it's all of a sudden goes away.
The record for the highest roller coaster is 6.3 Gs.
Yeah, it's actually not bad, yeah.
Before we
So
Where is
what
that
we're doing
one?
is generalizing it to any roller coaster that has a loop-the-loop. This is called a loop-the-loop, whether it's revolution or anything, right? And this is the same physics as
Oh, I
the
think
physics of getting a bucket of water and rotating it. I don't know if I have a video on
Is
that.
it the same physics as the space stations that rotate?
Yeah. Vertical.
Yeah.
Yeah,
Yeah.
exactly.
I can't-
And also the motorcycle. The motorcycle that was going like this.
Yeah.
Right, it's the same physics. I don't know if I have one, but
think
I should
the-
have
the
had
reason-
one where I get a bucket of water and rotate like this. I should make one video like that. And then at the top, the water does not spill.
Be a clear
Right.
bucket.
Okay, now the other one is the Colossus type ride, where you are always on the top. So it goes like this, like this. So here what you want to do is you want the velocity, the bottom is the same as the bottom of the revolution ride, but the top, you don't want to go too fast, because otherwise you'll fly off. Instead of you have to go fast, it's now you don't want to go fast, right? Because if you go too fast coming into a ride like that, you just go like this and then you crash into this, right? So here, what happens is that the equation is inverted. You have mg, you have n, and the acceleration is down, ac. So you have mg minus n is equal to mv squared over r. Okay? So then you have here n is equal to mg minus mv squared over r. So instead of mv squared over r minus mg, it's mg minus mv squared over r. So if the velocity is 0, that's okay, because the ride can stop there and you will not fall off because you're sitting right side up. So your n is equal to mg. But what's the maximum this kind of ride can have? And what's the maximum velocity? Then the maximum velocity you get by setting n equals to 0, you get square root of rg, n is equal to 0. So this is the same physics as the physics of the Ferris wheel. Ferris wheel. Because the Ferris wheel, you're always sitting right side up. Like that, right? happens here, as you're turning, the seat kind of rotates under you so that you're always sitting right side up, right?
Yeah.
But at the top, if it goes too fast, imagine this thing going very fast. At the top, if it goes too fast, then you're gonna fly off, right?
Yeah.
Whereas the revolution is the opposite. You want it to go fast so you don't fall, right? So the maximum velocity should go is square root of rg. So these guys can actually go faster because their radius is larger, right? So you have more of a chance of making it faster. Okay, cool. Okay, now let's start a little bit on a motion with the presence of air friction. People ask me, well, why is that put in this chapter? And I said, they couldn't figure out what chapter to put it in, so they put it somewhere. So it kind of could go anywhere, really. Motion in presence of air friction. So we're going to focus on cases where you drop an object, kind of like you did with that lab, where you drop the paper plate and then eventually reach terminal velocity, right? So you have an object like this, it weighs mg. So imagine its initial velocity is 0, right? And then now you drop it and then there's air friction on it, right? And air friction depends on the velocity that it's going at. So air friction is negative BV, right? So it's B could be any constant, right? And B would depend on the condition of the air, the thickness of the air, depends on thickness of air. So if you are in Venus, which has a very thick atmosphere, the air friction coefficient on Venus would be higher. If you're on Mars, the air coefficient friction would be much less because the atmosphere of Mars is very thin, right?
Or it would depend on elevation too, like
Huh?
the further we get away.
It also
up.
depends on the elevation because the further up you go, the air is less dense. And so the constant B also is changing. Now you gave me a good test question idea.
Damn it.
I'll give you a function. I'll give you a non-uniform function B as a function of the height. Ooh, thank you, Bart. Good test question idea. Non-uniform B.
Just want to know about
Wait,
big
why do you
bear.
make it-
You just ask me questions, guys. Fuel me. Fuel my imagination. Right? And it also depends on, a big thing that it depends on is on the surface area. On the surface area of the material. Right? So which one has more friction? If I drop this way, more friction, or like this? If I crumble it up, which one has less friction?
Second.
Crumbled is less, right? So when the surface area falling through is less, then is that thunder? Wow. When the surface area falling through is less, then depends on surface area. So the smaller the surface area, the smaller the B, right? How about this way? Falling this way versus falling this way. I'm not changing the surface area of the marker. I'm not crumbling it, but I'm changing the orientation, right? Which one has less air friction?
This one.
You see? So if the surface area is laid perpendicular to the direction of the flow, more surface area, right? So probably we should say depends on the surface area perpendicular to the direction of the flow. And then the units of the B are going to be newtons per meter per second or pounds per feet per second. So it's kind of plays the same role as coefficient of friction, mu k or mu s, but those ones are unitless. This one actually has units. So then what do we expect to happen? As this thing is falling, it's picking up velocity, right? And by the time it reaches somewhere here, the velocity is a little bit larger, so the friction is now starting to increase, right? If the friction increases, what's happening to the acceleration? The acceleration is starting to decrease, right? The initial acceleration is equal to g, because only gravity is acting on it. As it's going, the acceleration is less than g, right? And then it picks up more velocity. Eventually, the final velocity, what if it reaches a certain velocity where it doesn't actually accelerate anymore, right? So we have here BV terminal, and at that point the acceleration is 0. So when does that occur? When BV terminal equals mg, V terminal equals mg over b. So the terminal velocity that something is going at is equal to its weight over its b, right? So all other things being equal, if I take two markers, let's say these two markers, let's say their surface area is the same, and drop them in the same way, both of them pointing down instead of like this, but this one weighs a little bit more. Who should hit the ground first?
Hit the ground at the same time.
The heavy one.
Heavy one?
Yeah. Because the heavy
Oh, sorry.
one will reach a larger terminal velocity.
Sorry, my brain went back to physics 11. Sorry.
Yeah,
A
because
vacuum.
your brain is going back to, Galileo said everything
Yeah.
should fall in the same ground.
Yeah.
But that's if their air friction is ignored.
Yeah, that's true.
For a heavy object, if it weighs heavy, it's got to travel faster for the air friction to equal its weight. So therefore, the heavy object accelerates for a longer period of time. You see? Now, if we conduct the experiment, I can't tell the difference because the height is too short. So we got to go more up. Go to the Leaning Tower of Pisa, all right? Or maybe go to the E7 building. Let's see here. Huh?
I saw that one.
I'm gonna do it so that this one hits the ground first. Well, of course, I'm kind of faking it. I'm helping physics out here. I'm dropping this earlier. Oh, physics wins! Right? So you can skew the data to make it work, right? So the next thing we're gonna do is we're gonna develop the equations of how the velocity changes as a function of time, right? Well, we know if the acceleration is constant, for A is constant, we know that the equation is this. V final is V initial plus GT, right? Velocity increases linearly. Well, in our case, is the acceleration constant? No, because acceleration starts at g, but then it less than g, and then eventually it goes to 0, right? So if we have a non-constant a, so what's the equation of motion here? mg minus bv is equal to what? ma. But a is the derivative of v, all right? So we have here mg minus bv is equal to m dv dt. So what kind of a function is there, v, as a function of t, such that if I differentiate the function, it will give me mg minus bv, you see? So in other words, find the function v as a function of t, such that if I take the derivative of this, it will satisfy this differential equation. This is a, what is it called? One-dimensional separable differential equation, right? Is that?
Right. First order linear.
Yeah, first order linear differential equation. One of the easy ways to solve this is, since it's separable, you
Yeah.
can take this and put it on the bottom and take the dt to the top.
Right.
Then integrate it. Separables are easy because you can take this thing and you can put it at the bottom and then take the dt to the top and then integrate it from 0 to some v and 0 to t. Right? And then what's that going to be? T, m, what's going to be the integral of that? ln, right? ln of mg minus bv. But then because it's a bv, what's going to happen? The coefficient of the v, the term in front of the v, will come out but reciprocated. So negative 1 over b. Right? I'm doing it kind of in my head without doing formal u substitution. Just say, okay, this is a unit. You take ln of that, then whatever's here comes out and then it reciprocates. Right? And then you're going to cross multiply. Then raise both sides to the power e. Then what's going to happen? E to the ln cancels. So you have here mg minus bv, e to the minus bt over m. Right? And then my eventual goal is to come up with, isolate the v, so that I can come up with a function of v as a function of t. Right? So then I can take this to that side, bring this over to this side. Did I forget something? I feel like I forgot. No? So this one, mg minus s is equal to bv, right? Yeah, there you go. It wasn't working out nice. And now what I can do is raise both sides to the power e, right? So then you have e to the minus bt over m is equal to what? E to this power, so then you're gonna have what? The ln is gonna cancel. You're gonna get mg minus bv over mg, right? Because this is minus ln and it comes down to the bottom. Okay, now I can divide this. Take this there, bring that here. Cross multiply. And then you have the first equation here.
Professor,
Hey.
could you repeat the mistake?
Oh, I had to do the 0 to t and 0 to ln. So when you do 0 to b, it's not always that when you put 0 here, you get it cancels away. Right? So you have to put the 0 in here, and then you're left with ln of mg. So you have to deal with that. You see? So if you look here, or the formula sheet, physics 1, test. This is test 3. Yeah, test 3 formulas. So those are the formulas for test 3. And the formula that we just derived was this one. V of t mg over b, 1 minus e to the minus bt over m, right? This gives you the equation for v as a function of t in a case where air friction is affecting the material
quite a bit.
we
So
can-
then we'll talk about the rest
We can-
on Monday.
We can use the formula directly in the test. or-
Yeah, because on the test, this will be the first page
Oh, we
of the
don't have to
test.
prove that, right? Because I was kind of confused. Because I always prove the formula